All right, so welcome back from part one, where we are continuing our proof again about the path difference derivation of the fringes produced by the Michelson Interferometer. Now, to continue from before, I've only kept the actual important results, such as what the difference in the path of the mirrors that the observer sees, like how far away does the observer perceive the mirrors to be, and how far away does he perceive the images of the source to be, which is double that. We proved that in the last part, in part one. The source we were imaging was a point source, so the images are also point-like over here. And the only introduction I've made right now is this normal line to the actual mirrors, which we're going to use to, again, enforce the laws of reflection in just a second. So the difference here that we're going to do right now is we're going to replace this point-like source. We're going to replace it with an extended source, something like this right now. Okay, we're going to replace it with something like this. And the reasoning behind this choice is that if I'm shining a laser right now toward the beam splitter, the cross-sectional area of the light, that's coming out of the laser is not going to be a point. It's going to have like some actual finite surface area. It's going to look more like a disk, like in our case over here. So I want to see what happens when I image different parts of that disk that comes from the laser through the apparatus. Okay, I chose to image only one particular part of that disk. You could have chosen anything over here, right? It's not unique, the choice that I made. I made the choice of imaging this because it will look the prettiest, right? Because it's the furthest away from the optical axis. And it's just, you can see it better in this false 3D diagram right now. So you can choose any of these points to do the experiment, and it will work the same way exactly. Okay, so if we want to image this point right beside here, what have I done? What do I have a blue and a red here? Because each of these is going to be imaged through a different mirror. Like the red is going to be imaged through mirror 2, and the blue is going to be imaged through mirror 1. We're interested to see where the images of the same point there are going to lie when we go all the way out here. We're interested to see that. So we're no longer going to have the images be points or at the center here of this white line. Okay, so to begin, could we have a case where if I'm imaging right now through the first mirror, through the blue, could I have a case where I just have a ray like before and it's completely horizontal? Yes, I could. Obviously, the rays that come out of this could be in any direction. It's ambivalent. So would I be able to see the reflection of this though? Well, as the observer, no, because my eyepiece right now is too small and it wouldn't be able to see the reflection of this ray. Of course, the more I open up my eyepiece, the more I make the field of view available to me. And in this case right now, it would actually catch this. Of course, the eyepiece is pretty small in this experiment. So I would say size-wise, it would look like something like this. So I'm not going to catch a ray that looks like this coming from S over there. So my next ray that I can try and reverse engineer this and see what rays could actually go through the observer. The observer's eyepiece over here. And reverse engineering it right now, we can see if I bounce off right where the normal is, that green line, if I reverse engineer it, looks like something like this could do the trick right now. Something like this, if you can see here, like this is going to be a ray right now that I'm hovering that will actually make it through the eyepiece and I will be able to see the image of S. Okay. Now, we know that we are, again, off with that blue ray that I'm sending toward the mirror M1. I am off from the horizontal by some angle, again, theta. That's the idea. All right, but I can see a wonderful Z pattern over here forming, which means the angle, again, I have right there from my incidence angle is going to be theta. What do you know, though? According to the laws of reflection, the incidence angle needs to be equal to the reflection angle, so this guy over here will be theta as well. Now, where would the observer see the actual source appear right now? Would it see it like this distance behind the mirror? Not quite. So I'm going to use this line as a reference to draw where we're going to stop our extensions of the lines backwards, because this is going to be a little bit of a cumbersome process. But the observer here will see this S this far away. So we're going to extend this line backwards behind M1, but for a distance equal to this much. So let me show you what that would look like. That would look like roughly, again, that would look like roughly over here, something along the lines of this. Okay, so I'm going to try and line everything up the best that I can. So you see, the length of the extension line right now behind the mirror 1, I've made sure it's roughly the same as the path of the source point from mirror 1. So that's where roughly we're going to see the image of S appear from the reflection through M1. And I can put that over there right now. We can indicate that as a blue right now, and that's where this plane for my image would be, and the blue ring would look like this. The blue imaged ring would look something like this. That's this image through M1 over there. So that's where this roughly appears to be. And beautifully, we can see over here that the angle again of elevation here of this extension line with respect to the horizontal is going to be theta, since these angles are opposite. Because it is an extension line backwards, I'm going to dash it in so it actually looks like a backwards extension. I'm going to dash it in, and it leads to the virtual location here of that image of S. Okay, so this is like, we can call this, I guess, I1. Okay, so we've got that done. Now we want to see if we can repeat the same thing for mirror 2. So I'm going to shoot a ray. I'm going to reverse engineer a ray that again passes through that eyepiece right there. I'm going to reverse engineer it right now. So I'm going to reach over here right now where the normal is, and then I'm going to take that ray back and see how I could have it arranged. You can see my incoming ray from point S right there. Okay, they're supposed to be parallel, the blue and the red, but again, I won't nail it exactly due to the inconsistencies of OneNote and not using a ruler. But these, this blue and red line here that I'm selecting are supposed to be exactly parallel. So, you know, we're working with what the limitations that we have over here. All right. So we see again that we're coming in toward the normal. I'm going to fine tune here the edge of this arrow right there. And we're hitting the normal right now, again, with an incidence angle of theta right there. Of course, our reflection angle is going to be the same as dictated by reflection rules. And that ray, again, is going to reach our eyepiece and go through it, so we're going to be able to see it. But where is the image right now of S reflected from mirror 2? We're going to apply the same logic as before. So essentially, we're going to extend this line backwards behind the mirror M2, a distance equal to this guy over here. So this one's going to be a little bit harder, but I'm sure I can make that happen. So we're going to extend it backwards. We're going to make sure, again, this red line that I'm drawing right now is parallel to this one, and it has a length that is roughly, again, it needs to be exactly the same, but on here on the diagram, roughly will do. This length needs to be exactly the same length as this. So it's a little shorter right now. Need to fine tweak it a little bit. It's going to be like something like this right now. We're not going to go overkill on the accuracy. So the image right now of our source through mirror 2 will appear to our observer as it is coming from over here. That will be the top of the ring imaged from mirror 2. So I'll put the ring again in here as a whole that we're going to see. Okay, so just fine tweaking everything over here. That's what we're going to see. We've established earlier that the path again, the path between image 1 and image 2, this horizontal distance here is going to be 2D. We can reprove it again if we wanted to with the same arguments used in part 1, but I'm going to leave it here again as is because we already know that this is true. So the extension again of our red line, I'm going to dash it in so that it actually looks like an extension. So this guy out here, I'm just going to zoom in a little bit, needs to be dashed in because he is an extension behind the mirror. And it's not a physical ray, right? So we're dashing it in to show that. Okay, so now that we have that done, from our observer right now, he sees, so we got to make sure we understand this very well. He sees right now, from mirror 1, the image being right there of the top of our ring that we're trying to image. And then from mirror 2, he sees this. Okay? He sees this. And you can see that the white lines are approximately parallel right now. And the only difference between them, the only path difference right now, is this guy, this green line that I'm trying to put in right now. This is the only path difference. If I was able to calculate what this green line is right now, these remaining paths, like, let me highlight again over here, the remaining paths, this and that, would be exactly the same. So we would see no path difference at the observer's level. So it's just this guy that's introducing the path difference. And if we calculate him, that is the actual path difference right now that the observer sees between the two images, literally. So if I want to calculate again the path here, I notice that I can connect where I1 is. I can drop a line right now over here. Let's draw it in white. Okay, I can drop a line right there between I1, drop a perpendicular line down to the red extension. And you can see that this angle right now is 90. Now, we mentioned again that the length here is going to be the path difference that we actually see at the observer's level. That right there. So can I get this? I need one more piece of information, and that is an angle. Could we say something about this angle right here? Well, yes. Again, we can see this angle coming from the extensions here of the reflection from M2. This angle is also theta, since these are opposites, okay? And we observe one last Z pattern over here, one last Z pattern right there. You see it now. And that means that the angle inscribed over here is indeed theta. So since we have a right angle triangle, and I can highlight it over here for you to see, here it is, right angle triangle right now. This right angle triangle has adjacent side right now, delta P, and hypotenuse 2D, which means cos of theta will be nothing more than adjacent over hypotenuse. And if I rearrange right now for the path difference, all I get is 2D times cos theta. And that is, again, the full derivation of the path difference for extended sources going through and getting imaged by the mirrors of a Michelson interferometer. So I hope you find this helpful. If you do so, please give the video a thumbs up and consider subscribing for more of these complicated proofs to come. Thanks for watching.